Okay, so the first field that we're going to talk about today is the role of the student researcher in the lab. So with that being said, our first question is, what do you expect from a TAMS researcher in the lab? This can include lab activities, time commitment, communication, or just general responsibilities. And we can go in the same order as before.
Okay, I'll go first then. So we don't have a lab. It's my area, and most of my students' areas is pure math. So there is no lab involved. There is no specified office or workroom. What is expected from the student? This is kind of tricky because math is not a science. So it's have to be enthusiastic and want to work. I mean, it's there's no there's no specific times the students have to be anywhere, to be honest, and especially now since we hold all of our meetings via Zoom. During normal times, hopefully pretty soon again, they're expected to meet with the other members of the group, say once a week, and then keep in touch with the rest of the group, with the rest of the students as they wish, via email or whatever other means they feel like it. The important thing about the specific research program that we have is the interaction with other students, interactions with the grad students, supervising, advising the project, and working hard and being interested in what they're doing. So that's about it. That's what's required of them.
So I guess it's my turn. Before all of this happened, I would ask students to be in the lab about at least 2 days a week. Although I guess we can talk about that a bit later. This whole COVID situation has made things a lot more complicated. And we don't necessarily get to do in-lab research for everyone. So what I would ask of the students is you would start by shadowing the grad students, whether you're doing in-lab or remote work, and then pick up a specific technique that you can work on, whether it's computational, whether it's a spectroscopy, or synthesis. One critical thing that I think is really, really important for the time students, for being to be productive, but also for you to have a fruitful experience, research experience, is that you should think about analyzing your results, draw conclusions, and do your own literature research. So my hope for the undergrad students, also the time students and also undergrads, is that you're more than sort of a personnel that performs a given task, but rather you're self-motivated. You understand what is it that you're trying to measure, what is it you're trying to do, and what is the scientific significance of your task in the bigger picture of our research projects. So in a sense, doing a lot of thinking, a lot of literature research is emphasized in my lab. That's it.
So again, in our situation, we don't have a lab, and so typically what would be expected from any student, TAMS or graduate students, is to go through data reduction and data analyses processes. So it could be a certain mini project or a certain component of a bigger project, a bigger view of things. But essentially the way I interact with all of my students, regardless of what stage they are, is first off, I treat them as colleagues. They are my colleagues, no matter what stage they are. The only difference would be the actual way we interact. So for example, I would probably interact a little differently with a graduate student, expecting them to know a little bit more, to have a little more experience and a little more background, whereas with, for example, an undergrad and or a TAMS student, I definitely take into account the fact that they're very fresh, they're just starting to learn. I think another important aspect is that we expect students to learn from the projects, not necessarily to make groundbreaking discoveries over a 3-month period of time in their very first research, but mainly to learn about the process of science. And again, it doesn't matter, in my opinion, whether they worked in astrophysics, in my field, or whether they worked in Oliviero's field, or in theoretical physics, or in chemistry, or anything else. The important thing is that they gain the skills of performing experiments or observations or data analysis, that they can run proper statistics, reach conclusions, summarize the results in a report or a mini paper, and be able to present the results if and where needed. So once all this is taken into account, I'm very happy with the interaction with any student. Finally, I'll just say that I also expect students not to come to their professors as an empty vessel waiting to be filled. And I see that a lot, unfortunately. I see students, whether undergrad or grad, coming over after a couple of years of research and saying, okay, what do you want me to do next? And there are several problems here, because first, I don't want you to do anything. It's what you, the student, want to do. The other thing is you probably have some idea of what you want to do. I mean, if you came in fresh as a TAMS student, you must be passionate and fascinated about the topic, so you must have some idea of where you're going, and you want to gain more insights from your professor, from your advisor. I'm just your advisor. I can give you directions, I can give you some support, I can give you some advice, but I'm not your boss. I'm not gonna tell you what to do. This is a very important aspect. Thanks. Olivier, you're muted.
I completely agree with Ohad, and I was going to say exactly the same thing. So let me start from what I expect in general in my lab. So I have a lab, despite the fact that we are a computational group, but nobody is here right now because of COVID. So I expect people to join the weekly group meetings. So we have 2 meetings internal to my group in which we just update everybody else about what we've been doing. And these are the occasions where I really like people to interact and get feedbacks or motivation to do things. And then we have one group meeting that is shared with the group of, as a matter of fact, Hao and Dr. Jan and Dr. Cisneros in chemistry, in which we present research, and it's a good opportunity to see orthogonal fields of research. So I expect that as a minimum. But then in terms of work, I completely agree with what Ohad said. So I expect the students to be proactive. So we can't, I mean, we can give you a motivation, we can give you an idea, but I mean, the way the research works in my lab, I don't have, let's say, simple menial task that you need to learn and then repeat over and over. You need to understand, I mean, you need to have a goal, and you need to try to figure out the solution for the problem yourself. And if you are stuck, that's when you are supposed to contact me or contact the other people in the lab, ask for help, or, I mean, you are totally free to work out the problem by yourself. I mean, in research, there are a lot of, I mean, there is not one way of doing things. I mean, there are people that are really good at figuring out the solution by themselves. It's very easy to get stuck. So I think it's, I mean, the interaction with your more experienced colleagues is the way to solve a lot of problems. And sometimes you may be afraid that people interfere with your work or try to steal your work or don't understand what you are doing. But I mean, I think the best way is communicating. The worst thing that a TAMS student can do is stop being interested in the project because he doesn't know how to figure out the solution by himself. So if that happens, you should talk to someone, a graduate student, a postdoc, your advisor. That's something that I think it's really important.
Thank you all for your responses. Our next question is, how has COVID-19 impacted the lab experience, and how have you transitioned to remote research?
Badly. So, like I said, we don't have a lab, but human interaction is in the basis of research, at least for me. It depends. If there's this project that's been going on for the last 6 months or a year, then having weekly meetings or bi-weekly meetings is fine. But starting a new project, it's kind of hard. I mean, you need those 3, 4, 5 meetings to start with, with you, the students, the grad students, everybody just kind of sharing ideas, getting to the blackboard and writing stuff. So to start a project just using Zoom, it's possible when we're doing it, but it's much harder. But I think that, again, for me, and I'm guessing for most of the students, it's the lack of personal interaction. This is kind of devastating. And I agree with everyone said that research is fun, and this is what we do for a living, and this is what we like doing. And suddenly you're kind of sitting alone in your home. As you can see, I'm at home, and you can keep on doing the research, but you're missing a huge element of this kind of personal interaction, having fun together, just being together with others, with your colleagues, with your peers. This is very hard. In terms of research, it's fine, but in terms of, especially if you're just starting, and then realizing how fun it is to work in groups and how fun it is to do those things together, I think this is, for me, this is the thing that's lacking the most. That's it.
Yeah, for us, it hit us at a rather inconvenient time. I started last fall, and we got all our cool toys in the lab, and then we were told we should not come in. So this was quite a shock to all of us. We pivoted a little bit. I was really lucky that I'm surrounded by an excellent team of computational scientists like Oliviero and Dr. Cisneros. So we picked up some computational projects that students can work on remotely. The philosophy, I would say, of this group is that we want to push experiments and simulations at roughly at the same kind of speed, so that one don't get too much ahead of another. And right now we are, for most of our projects, falling behind on the experimental part. We're beginning to pick up momentum on that now that we are able to come back to lab and work a bit more than before. So for most of the projects, we are trying to push on the experimental side and try to catch up with the experiment, with the computational side. That being said, we are trying to explore a few different new things with our computation, because it's always easy to, I guess maybe Dr. Aljisi will disagree with me, but for some of the things that we do, it's easier to compute or calculate or simulate it in computer first before we go to the lab and try to actually do experiments. So we have a few computational projects where we're really trying to explore new things, try new computational methods, test the new systems, or just to try out a new idea. So that's how we have been trying to cope with the situation. And if you talk to some of the TAMS students that are already in my group, you'll find that they have, I would say, different experiences working, remotely and communicating through either Zooms or Teams. Is definitely not as easy and as enjoyable as in-person experience. But we're trying to sort of navigate through that. That's all.
For us, for astronomy, I think the pandemic not only held back research, it actually helped us a lot. On one end, the research has been flourishing. We've got one paper published in the group, and another paper just recently submitted, a big project submitted Many other projects are progressing on schedule, so we're doing great. In fact, we even recruited the other astronomer in our group a few months ago, all virtually for the first time. It was quite an experience, but we managed to do all that in spite of the pandemic. But I'd like to raise another aspect that I think is rarely discussed. I do feel in my group, since again, I'm interacting with younger people who suddenly, had their entire lives changed. Well, we all experience that in the same way, but for the younger generation, I feel that the change is more drastic. And I'm more concerned not about the physical or the more tangible and research aspects of what we do, but more on the mental effects of all this. And I can even sense, again, even though I'm not from that profession, since again, I'm working with younger students, I can sense the frustrations, the mental impacts that this pandemic is causing everyone. Not everyone has those bigger homes where they're flexible to do everything they want. Some students had to go back to their parents. Some even had to go back home internationally and work from there. So there are limitations and obstacles to overcome. But one thing that I do is I spend hours and hours trying to encourage my students that everything is fine, it'll go away, the sun will shine again, and we'll all go back. And I agree, human interaction is super important. We're all supposed to go to a meeting in Phoenix in January, and that one again has been canceled and will be done virtually, so it's not the same experience. I spend hours with my students, not only during our regular weekly meeting on Tuesdays, but also on other times. And I feel like a great deal of that time, a larger and larger portion of that time is devoted to, if you want, mentoring and psychology, how to cope with things, how to deal with this situation. And what I always tell them and encourage them is I say, look, you have really nothing better to do right now but to do research, because in our business, quote unquote, we sit in front of a laptop or a computer and reduce data, analyze data. The data are served to us. Gone are the days when the astronomer goes to the telescope. We can't do this in space anyways. But the analogy is we no longer cook our meals. Our meals are delivered to our doorstep by DoorDash or Grubhub. So we really, all we need to do is sit in front of our computer and reduce data, analyze data, write the paper, do some workout, do some physical activity, keep our minds going. But really, this is an excellent opportunity when you have nothing else to do, is to make progress in research.
For me, I think in general, I should be saying things similar to Ad, in the sense that computational science is clearly one of the topics that can be easily performed without a physical lab. On the other hand, there are several issues that make the experience now different from what it should be. And in my lab, we have a common room with an espresso machine. I'm Italian, and I basically take espresso breaks every 2 hours during the day. I drink about 5 espressos a day when I'm in the lab, and I expect the group members to somehow share this experience, because then we talk about everyday things, university things, and research things. So I think these kind of bonding moments are important in the research experience, because sometimes these are also the occasions where you come up with solutions to your research problems, or with some advices on your research path. So all of this is gone. And related to that, the fact that the student needs to be proactive in his experience, it becomes more challenging in a Zoom environment, because clearly you may not interact as often. If you come to the lab, then there are more ways of interacting, and mentoring is easier if you are physically here, because then maybe there is something that you don't understand, you come to my office and maybe I explain it to you. If you are at home and we are not synchronized in our schedule, then it may be difficult to get this extra feedback. So I think that may pose a problem, especially if you are starting with little or no experience or skills in the field, because it becomes much more difficult for me to train you on the basics.
Right, thank you all. And to finish up this section, our last question is, what experience or prior knowledge should a student have to join the lab? This can just include skills, specific programming knowledge, or things like that.
So I think it's kind of difficult. I think that Hart said something similar to this. I mean, that we get students from, they can be either TAMS students or freshmen up to advanced grad students. So it's kind of difficult to exactly set up the bar, what they need to know when they come in. We always try to work on projects in which we start from almost scratch. So, and many, basically all the projects, and then at some point split up to different other projects, depending on skill level and enthusiasm and prior knowledge. To start a project, you basically need to know, I wouldn't say nothing, because people say you know nothing, but you actually need to know something. I mean, so you're supposed to have some kind of good understanding of basic math, and the most important thing is math maturity, which is kind of hard to quantify, but one of my professors back in Israel said that mathematic maturity is being able to read a paper and realize you don't understand anything, not be intimidated by it, and then spend another 3 weeks just to figure out what the first paragraph actually means, and not just saying, you know what, the heck with it, I don't understand anything, and just go away. So mathematical maturity, and I guess I'm saying mathematical, I'm sure it's true for physics, I'm saying it's true for any science. I mean, just being, okay, I'm not stupid, that's fine. I'm reading it. And by the way, it's the same for me. When I read a new paper, which is not something that in the tiny neighborhood of what I actually do, it's like reading another language. So just sit down and read carefully and spend by far more time than you think on just understanding it and not being intimidated. So I'm guessing what you need is mathematical maturity and, or maturity. But at the end of the day, it's just about really being enthusiastic and curious and interested in what you're doing. What's the phrase in English? So the cow wants to give more milk than the calf wants to suck. I don't know if there's an equivalent to this in English, but basically I'm sure that all of us want to give by far more than students are accepting. So we want to give. And so it's enough that the students come enthusiastic, interested, motivated, hardworking. Basically, that's enough. That for us, at least. That's it.
For my group, if you get to do some in-lab research, then apparently you need to know your way around the lab. You don't have to know, all the specific techniques that we're going to use. Those are the things that you're supposed to learn here, but you should know basic lab manners, how to be safe, what would be the basic safety protocols in a chemistry lab. If you are to do remote research, then I would say knowing your way around the Linux system and knowing a little bit of coding would certainly be helpful, although not exactly required. The one capability that I would highly value, merit, is there's this concept called internet literacy. I don't know if you know about this. It's really kind of means you don't have to know every bit of knowledge, but you have to know where to look for it. Especially in the information age, we have so much information around us. Trying to trace down and find the right piece is more important than knowing that bit of knowledge in your head. So by extension, I think something like that is maybe I can call it literature or prior knowledge literacy. If you are asked to say find just example, the heat of vaporization for a certain compound, you would know where to look for that. That is something that I highly value for a student, especially for TAMS students.
Yeah, so I agree exactly with what Leo and Hao just talked about, and I would just add that I really don't expect anything from my students, especially not from someone who's coming in fresh, like a TAMS student. Obviously, you need to have some you know, math level or some interest in the STEM fields, and typically this is already served by your personal enthusiasm. So if you came to me to look for a project, it must mean necessarily that you're enthusiastic about astronomy, about astrophysics. You've read somewhere about black holes. I get this all the time. I get folks coming in saying, I read Stephen Hawking's book. I'm interested in black holes. I want to do some research on it. And I tell them, okay, sit down and listen. It's not that simple, but let's get you on track. There's a lot of reading involved. And again, don't be intimidated by what you read. If you don't understand something, you can always come over to me via Zoom personally. You can discuss it with my students. Again, we have those group meetings, and those group meetings are just about that, discussing topics that are of general relevance or general importance to everyone. One other thing that I would just add on top of all the good things we've heard so far is that I always tell my students, look, don't worry, just start, you're in good hands. You don't always know exactly where you're going. Sometimes these things are more adventurous than others. For example, if you're a graduate student, you can start with some idea, but you don't really know how it will evolve. If you're a TAMS student, it will be likely more focused, more straightforward. I don't want to say trivial. But I will provide you with all the tools that you need. I will provide you with the software, with the intro to the software, with the basic knowledge on the cosmological parameters that you might need. And to convey that message in a short video, I think it's a 2-minute video that anyone can look for on YouTube. And this, all of my students know that, because as soon as they walk into my door, I show them that video from a high-tech company that shows you how they build planes in the air. So they build the planes while they fly them. And I think this is my motto in my research in general. You embark on a project, you only have a few items available to start your project, and you gain knowledge while you're building your project and while you're testing it, while you're doing it. You don't always wait until you build something before you fly it. You build while you fly. While it seems kind of dangerous and not true in real life, this is how we run our things in my group.
So in my research lab, the idea is that you can pursue 3 different kinds of projects related to methods or software development or applications. As a newly coming student with maybe not too much experience, I would expect the application side to be more accessible, regardless of the specific direction. So clearly the direction depends on the passion or the skills of the student. Regardless of the specific direction, there are like 4 sets of skills that the student should acquire along the project to become, let's say, proficient in the research. And I mean, if some of these skills are present from the beginning, everything is easier, of course, but it's not a requirement. The main point is, as I said before, is realizing when you lack a skill and asking for help in that situation. So the 4 set of skills are basically knowing how to use a Unix-based operating system. So using a Linux computer or a terminal on a Mac computer, because all simulations in my lab or in general in computational science are run on Unix-based systems. And so there is a bit of a learning curve there. It's nothing particularly strange, it's just learning commands. If you know that already, it's great. If you don't know that already, I mean, I'm willing, and most of the lab is willing to help, but you need to ask for it. Then programming is clearly a plus in a computational lab. If you know Python, it's great. If you know Fortran, which probably you don't because it's not very useful for, let's say, non-academic researchers, it's even better, but I mean, it's not needed. But at the end of your studies here, you probably will have learned a bit of Python. Being able to do a literature review or finding literature material related to the topic that you are studying is something that you will learn as you progress in research. if you know a bit how to do it before, it's clearly a plus. And then eventually you will learn something about the physics or chemistry of the system that you study. And again, in that case, if you already know, if let's say, if you want to study a protein and you already know the basics of biochemistry, it's easier than if you start without knowing what an amino acid is. Again, nothing of this is mandatory to start, but especially in the current situation where mentoring is more difficult because of the Zoom environment, the more of the skills you have to start, the easier it gets.
Thank you all for your responses. Our next few questions concern life as a researcher as a profession. So our first question is, what advice would you give to a student planning to go into research for a career?
Probably don't. No, I'm kidding. So it's a marathon. So it's not a 100 meters dash. So this is, I think, the most important advice. And maybe even a cross-country long run. In the good sense, I mean, I can tell only from my own experience and my friends' experiences. It's one of the best environments to work with and to be around. I mean, you're surrounded by people who are brilliant, and most of them smarter than you are in whatever you're doing, which is nice. I mean, so you're surrounded by the best people in your field. You're always learning. So, and I'm not saying it as a kind of a, no, I'm learning every day something new, but you are learning every day something new, and you're learning from the best. The advice is to take it easy. I mean, it's kind of, like I said, it's a marathon. It's a long trip and adventure. And so, and be sure that you really like it, because if you're doing it for the fame, there's not much fame in it nowadays. I mean, it's I don't know, maybe not in math anyways. And you can make a better living doing other stuff. And no, I'm serious. I mean, I'm serious. I mean, so you have to do, it's like, okay, let me be a little bit more kind of poetic and philosophic. Math, I mean, I guess science is just like art. I mean, most of science and definitely most of math is not needed, you know, to come up with a new, you know, iPhone. You don't need it. I mean, don't believe what they tell you that you actually need math in order to get. I mean, the math that is needed is basically done in the 18th century, maybe the 19th century, and whatever you need for technology. You don't need the math done today. Nobody's using it. And so just like art, I mean, you can live without art. I mean, the world would be okay without, I don't want to start name dropping or something, but, you know, without the most famous artists or musicians. But it would be a pretty dull world without those things. So you should, if you really want it, if you really like it, then you should do it and be prepared for a long and very exciting and, you know, adventurous trip. And the life of, again, from my own personal flavor, life of being in research is amazing. I mean, not only do research, but you interact with, you know, young people, I mean, on a regular basis, all the time. You make amazing friends. And my advice is, so bottom line, do it just because if you really want it and you really enjoy it. That's it.
Yeah, I completely agree with your. It's you need to really love it to be really good at it. I just want to add one point. The love of research, I would say, especially fundamental research, from my experience, is a how do I say it? It's an acquired taste. It's not something like, you know, hot chocolate on a winter morning that you would appreciate immediately. And for a lot of us, myself included, many of my colleagues that I witnessed, their first research experience could be utterly miserable. You don't know your way around, you messed things up. But if you feel like there's something that's kind of satisfying, something that's, may I even say, kind of itchy that makes you want to find out the answer to a question, if you find that in your heart, then I would encourage you to stick around a little bit longer and just keep on trying a few more times. You get better than faster than you would expect. And over the time, this can be a rather satisfying and in a sense, even I would say addictive hobby that you'll pick up. Trying to design something to figure out a question is, in my opinion, there's nothing more satisfying than that. I would also say that, yeah, this is not a sprint. It's more like a marathon. So don't burn yourself out at the beginning. Yeah, that's all.
Okay, so the one advice or my 2 cents in all of this is the following. If you're not absolutely enthusiastic about STEM or about anything, if there's not a flame burning inside of you that tells you, I need to go and do this, don't do it. It's true for art, as we all mentioned. It's true for anything. I think that what you're seeing on the screen right now with the selection effect, you're seeing 4 professors or 4 professionals who, for the reason why they're there on the screen is because there's something burning in them, the burn of knowledge to do things, to figure out something in math, a problem in physics, or a problem in chemistry, or achieve something. If you don't have that burning desire daily when you wake up in the morning and when you go to sleep at night, or if you can't fall asleep because there's some physical scientific problem that's bothering you, you're probably not on track for a research career in STEM. And don't get me wrong. I mean, you may be very talented. You may be extremely good in what you do. Your grades and all, your GPA might be amazing. But if you don't have that burning desire, don't try to go that path, because one of the things that are really devastating that I saw a lot throughout my career is people who came over, let's say came over to me and wanted to work on a research project or wanted to work within astronomy. And soon enough, you realize that they don't have that burning desire that's needed to be successful. In other words, they have been likely pressurized by someone or something, or maybe someone set expectations to them that were way too high. Like, and you probably, we all know that, right? You need to be a doctor, right? Your parents tell you, or your grandparents tell you when you're very young, or you need to be an engineer when you grow up. Well, maybe what if you don't want to become a doctor? What if you don't like to be an engineer? Just do what you're passionate about. If you're really, truly passionate about astronomy, let's talk. If you think you want to do astronomy because you saw Neil deGrasse Tyson on TV, or if you're older and you saw Carl Sagan on TV, that's probably not the right thing to do. So keep that in mind in whatever you do. You know, just to give you some examples from myself, you know, as an amateur astronomer, I started off when I was, you know, a teenager or less than a teenager, about 40 years ago, and I, you know, wanted to get my first. I asked my parents to buy me my first telescope. I later evolved into a place where, you know, I couldn't fall asleep because of a certain problem, a physical problem that bothered me, or I used to wake up in the middle of the night figuring out where my bug is in my script, and wake up at 3 a.m. and go fix it. If you're that kind of person, you're on track to a successful research career.
So I think all of what has been said is correct. So it's a marathon, and like many other fields, like arts, I'd say sports, acting, there are activities that we all sort of like instinctively. And I mean, the problem is that chances to arrive at the desired position are as slim in research as they are in professional soccer or in Hollywood acting. And I mean, and that's not an exaggeration. So the number of people pursuing PhD degrees versus the number of faculty positions available are more or less in the same, in that level of percentage. And it's a challenging selection that depends on many factors. And I think you need to be really motivated to go through all these experience. So you end up, I mean, and there are a lot of, I mean, as in life, there are a lot of things that happen that can affect this. There is luck, there is your motivation. So it's, I think, I mean, research has a lot of advantages. I mean, it's not that we get paid like an Hollywood actor, but we get to do, like, we get to study something new all the time, and I love studying. We get to interact with brilliant people, go to conferences, and teach young, motivated students. That's a great part of all of this. I mean, I love sharing what I learned with other people. So I think it's challenging and can be challenging and frustrating. So be prepared. That's my main advice. And I stayed in research after my PhD for 10 years before starting my position here. So if you are really motivated, you can survive long enough to land a good opportunity. But again, I mean, there are different situations, and anything can happen. So.
All right, thank you all. So now we're about halfway through our questions. So we'll go ahead and flip the order so we can start with Dr. Andrusi and end with Dr. Fishman. So that brings us to our next question, which is, what was your very first research experience like? Did you experience any challenges or setbacks, and how did you overcome them?
So are we going in the opposite direction? So I start, or?
Yes, you can start.
Okay. So my first research experience was as an undergrad. I did my studies in Italy. When I did my studies, the undergrad in Italy was 5 years long, so it would roughly correspond to a master degree here. And so I basically finished all my exams in the university 1 year early in order to have the last year just for research. And I did it in a group that is pretty famous in its field, so it's computational chemistry. And he was, so I had an official supervisor, which was this old boss, very famous chemistry professor. He had an assistant, which was at the time an assistant professor, which was a young lady, was very brilliant and very helpful with the practical things. And then I was supervised by another student that just graduated in the group. I think it was frustrating in the sense that as a, let's say, very motivated undergraduate student, looking forward for 1 year of research where I would discover something new and impressive, I kept thinking that what I was doing was nothing really spectacularly new with respect to what other people have been doing just before me. Like the work of this PhD student that just graduated looked like so much more innovative than the project I was working on. And so I sort of started being really somehow settled back by this fact. I kept finding issues why what I was doing was not as impressive as it should have been. At the end of the day, I mean, the publication that I got from that work is still one of the most cited that I have. And so the work was actually quite impressive for an undergrad, I mean, thinking at it now. But clearly, I sort of expected more than it's reasonable to expect in this field. I mean, nowadays, research is so specialized that it's really, really difficult in many fields to find something new without like some years of research on one topic. So, I mean, you hear about these geniuses or phenomena that discover something new. Most of the times these are like fake news. I mean, it's they made a small contribution or a small part in a work that was already in the right direction to begin with. So, I mean, it's nice to be motivated, as Oad was saying before. It's what keeps us going and what will lead you to a research position, but don't expect to get there immediately.
Okay, so as an amateur astronomer, I was continuously involved in research projects on my own, mostly low-key research projects that I did either by myself or with colleagues of mine who were also amateurs at the time. The nice thing about astronomy, by the way, is that you can do research even as an amateur, cutting-edge research, in fact. But I would mention here perhaps my very first paid research opportunity, which I will never forget. I was an undergrad in the early 90s, and then I teamed up with a researcher at Tel Aviv University. Basically, I went down to the WISE Observatory of the Tel Aviv University in the Negev Desert in Israel to test the seeing, basically the blurring effect of the atmosphere over the observatory down there by looking at binary stars and trying to see whether I can resolve them. In other words, I looked at wider binaries and binaries that are closer together to see where my resolution would hit a limit. And I was quite happy with that experience. It was all naked eye observations that looked very primitive, yet they were important. It was a lot of fun, and I got paid for doing that. I was truly happy. Although later on, of course, I became more and more involved in bigger and bigger research projects as a graduate student, as a postdoc, and eventually as a professor here at UNT.
I first started working in the lab when I was a sophomore, and I can still remember my first project. It involved a furnace about a feet long by about an inch wide. We flow some methane gas in there, and on the other end, you collect a whole bunch of black soot, which, if you do it correctly, you get some carbon nanotubes, which about 10 years ago was a pretty hot topic. So I went to this professor, who was my first advisor, and I said, I want to have something to do with your lab. And he said, yeah, go ahead, follow this grad student. He knows how to run that. You work with him. So for the next about 3 months, I spent about 3-4 days a week, about 12 hours a day, working around that furnace. I ended up feeling like I'm working in a steamer boat with my hands and sometimes my face covered with soot. And for some reason, that didn't scare me away, and I felt even a bit fond of that. And I get to learn a bit more about the subject, what it is that's in that black suit that got people excited and want to invest in that. And I would say ignorance is bliss at that time for me. And I started to kind of daydream, hey, I have a small tube that's only a couple nanometers in diameter. What can I make of that? So I kept daydreaming for some time, and turned out most of the ideas didn't work. But I think what I got from that experience is one sort of a assertion that I'm not afraid around experiments. I'm not afraid around failure. I'm not afraid around working with unknown stuff, and it has a exciting factor to it to me. So that's sort of one of the first signs that I have put for myself that I might want to go into this career, research as a career. The second thing that I took from that experience is really a taste of what is good research versus what is not good research. I was lucky to be mentored by some of the best chemists that I have, how shall I say, contact with or access to back at that time. And it's not really the specific techniques, the tools that I learned back then that I kept on using today. Most of them, I have already forgot. But it was really a discussion or a taste of what consists of a good scientific question that I begin to develop back then that I think is really benefiting, and it has a long-lasting effect even to the research I'm doing today.
So my research is slightly different, I'm thinking. So as a master's student, I worked on my dissertation alongside my advisor, who was one of the leading figures in logic and set theory at the time. This was in Bar-Ilan University in Israel. And then it was pretty exciting, and I was really happy about it. And I thought that I really understood whatever I was doing. And my professor left academia for personal reasons. And before he left, he suggested that I go to the Hebrew University and continue there with another professor, Saharon Chelach, a very famous mathematician that is in Jerusalem, continue in logic and set theory. And so I went there and sat with him. And after sitting with him for about half an hour, I left the academic world for about 10 years, realizing that there's no way I can do this. And so I totally left. And I started a career as a teacher. Much later, I mean, it was pretty devastating. I mean, because I thought I'd use something, let you sit down and talk to this person and just, okay, I'm out. And so I came back to yet a different university, so in Beersheba, in the Negev. And I said, okay, I'm not going back to logic and foundation because this is too hard for me. So I started doing some other stuff, some other research in number theory and dynamics. And the thing that I got out of this, that never go back to logic and foundation because it's too hard. Apparently, so the funny thing is that, and I came here, and I don't know if you know this, but the math department has some of the best logicians in the country. And so I came here, I said, okay, I should overcome my fears. And my first research, so my first paper is actually in logic. And it took me quite a while to get over this devastating, it's kind of, you know, it's very kind of euphoric. And you publish a paper, it's read by others, you get comments. So it's really nice. And then you think, okay, I can do this. And then you realize, well, maybe not. And then so for me, and now I'm going back to, as I'm kind of tying so going back to logic and foundation, and now I continue to work on it. But what I took from it is, first of all, that so some students come to me and they say, listen, I failed this exam, or I failed this, or I left the academia for 2 or 3 years, I'll never go back. Well, you know, I'm not impressed. I left for 10 years and I came back, and I came back as a grad student at the age that most of my professors were younger than me. Actually, one of my professors was a former student of mine in Hebrew University. So I just think this is fine. And this is going back to what we said before. It's not a race. I mean, and you should really love it, and you shouldn't care about anything, and you should just continue if you love it. And I confronted my fears with a topic that basically broke me, and now I'm actually working in the field. So I don't know. It's you know, we described it as a marathon before. It's actually even more involved. It's kind of a spiral thing. Sometimes you have to go back. Sometimes you go back, you go forward, you go up, and you go down. But the thing I'm taking for this is that I should have continued then. I should not have broken down and left for 10 years. I should have continued, but you know, all's well that ends quite okay. Not really well, but it's fine. Thank you.
Thank you all for your responses. So our final question is about your personal experience with research. So the question is, what was your most fun or interesting experience throughout your research career? Or what was your most difficult experience throughout your career? And what insights did you gain from that experience?
Sorry, it's me again, I guess. I was distracted by looking at one of the questions in the Q&A. Can you repeat me the actual question?
Yeah. So what was your most fun or interesting experience throughout your research career? Or what was your most difficult experience throughout your career? And what insights did you gain?
So those were the questions where I was not sure how to answer when I saw your list of questions. I think So difficulty is again trying to, so one of the problems that I had as a PhD student is, or even earlier, it's comparing with research of other people. So it's kind of frustrating, especially if you are part of a big lab that does a really state-of-the-art research, and you have surrounded by like brilliant, very smart students or postdocs. It's sort of, I mean, it can easily become frustrating if you feel like your contribution is not as important or not as cool as other people are doing around you. And so I think one of the most difficult things is to grow up enough to detach yourself from the competition with the others. So if you are aware of the fact that what you are doing is important, and that you are probably one of the few people that is able to do it, and you pursue your goal in a rigorous way, then eventually the results will come, and science or publications will prove that what you have done is a good contribution. People will cite you. I mean, sometimes it takes time, but at the beginning it's really frustrating when you do something and then you see other people close to you publishing like very high impact journals, or you see competitor groups publishing very high impact journals, and you question yourself, why didn't I arrive at that solution myself, or why didn't I do it sooner? At the end of the day, I think the most important thing is to realize that you have to do your work and worry about you can do, and try to detach as much as possible from what, I mean, sometimes it's just an impression. It's like your judgment of what you do is always hypercritical, and then you realize that what other people have been doing is BS, and you know it because you have spent 2 years doing it, and then at the end you managed with some ways that the other people haven't found, and you realize that what they published is probably not as good as what you have done. So I think that was it was challenging. During my PhD, I was really frustrated, and it took some time.
Okay, so I'll speak for a couple of minutes about my most fun research experience, although I have to say that I have fun research experiences almost daily. I have some frustrations as well, like all of us, but again, I think that, and again, I'm truly biased about astronomy, so astronomy really tells us something new every single day, and you know, there's almost no competition because there's so many things to work on that there's enough for everyone, and maybe even more astronomers. I would also add, following one of the previous questions, that I consider my job, if you want to call it a job, the dream job, because I really get to do everything that I like. Everything is nice, environment is nice, you interact with young people, you do what you're really fascinated about. And in fact, some of us would say in the astronomy community is that we're basically getting paid to practice our hobbies, right? Because this is our hobby, it's not really our job, and we do it because we love it. So here's one example of what I'm really proud about. That is an experience from about 25 years ago as a graduate student, again, running some Q observing. Q observing means you observe not only your targets, but targets for all the community at that particular night, all the visible targets during that particular night at the WISE Observatory in the Negev Desert in Israel. And I come across a field of view in some dwarf nova, some variable star, some cataclysmic variable star. Again, I'm an extragalactic astronomer. I'm not supposed to care about these objects, yet I observe them for someone else, a graduate student at Tel Aviv University. And suddenly when I look at the finding chart, I noticed that there was something wrong. For a few minutes there, I couldn't figure out what am I looking at, because I'm usually pretty good at it. I look through the telescope, I look at the image on the screen, the CCD image on the screen, and I'm pretty sure I know what I'm looking at, what the star pattern is, and what the object of interest is. But in this case, I couldn't. I looked at the finding chart, a printed version of the star field, and I was looking on the screen, and it just didn't make sense until I realized that one of the objects in that field had moved a little bit. We call this proper motion in astronomy. So one of the stars, not the star of interest, not the object of interest, but one of its neighbors, had moved just a tiny bit since 1955, the day when the finding chart was taken from a photographic plate. And I think it was 1995, so about during the 40-year period, that star moved a little bit. And when I say a little bit, is about a fraction, a small fraction of an arc minute, okay, or maybe a few arc seconds, not more than that. And that tells us that we're looking at a very close nearby star. So I didn't decide to stop there. I said, I'm going to pursue this. It's beyond my line of research. I'm not going to get too much credit over it. I'm not in that field of research, but I'm still going to pursue that because it's interesting and I can do that. So I did a lot of reading. I also added spectroscopy to this research, and I knew nothing about spectroscopy at that time because no one taught me how to do that. And I urged one of our graduate students, perhaps one of the only 2 people at Tel Aviv University who could really do spectroscopy, can you please join me one night at the observatory and teach me how to do spectroscopy? We did that. I did the research pretty much all by myself and published a paper about the discovery of a nearby M-dwarf star, one of the closest stars to the sun, perhaps the 20th closest star to our sun, which again is not terribly amazing, definitely not at the end of the 20th century, but it was a pretty cool discovery, I thought, and so did my colleagues. They thought the same thing. And again, I knew nothing about the subject matter. I wasn't terribly interested in it, but I thought it was cool. And as evidence to that, many years after, one of my colleagues who knows me as an extragalactic astronomer asked me, hey, I saw that on your CV you had this strange paper on your list. Did you really discover a nearby star? And I said, yes, it was me. It was fun. I did it as a side project. I was just so curious as a beginning graduate student that I just decided to follow this track. I had the resources. I had the good colleagues to ask questions. I was really curious about it. Again, I wouldn't fall asleep until I finished the analysis, and I did that and I published it. And I think this is what showed me, and I think others, that when you're really passionate about something, when you're really curious about something, no one's going to stop you. Just continue to pursue that, work on that path. You know, ignore everything that you hear around you. This is not for you. This is not going to get you credit. This is not going to get you land you a faculty position. Just keep on doing what you're passionate about, and you'll succeed.
I thought that I can share a rather specific example of a piece of research that I did that was both miserable in the beginning and eventually kind of enjoyable, and have this kind of eureka moment. So this happened when I was in grad school, and at that time I took up this task of designing a memory device, memory in the sense of the memory you use in your laptops, etc. And we came up with this a new material. Long story short, it's supposed to have a so-called hysteresis loop. You can just imagine it as a circle. And when this thing turns clockwise, that's when we have the sign that this thing is working correctly. And at that time, for about every 10 devices I may have like 1 or 2 of them that have this right hysteresis direction. It turns clockwise. For the rest of them, they did the opposite thing. They turn counterclockwise, or they don't have a loop at all. And that frustrated me for about 1.5 years. No matter what I do, I changed my experimental parameters. I engineered how I synthesize this, how I stack them together, how I assemble them, how I measure them. Nothing worked. Out of 10 devices, I may have 1 or 2 that worked in the way that I expected, and the rest of them had all kinds of weird behavior. At that point, I start to realize maybe there's a counter effect that wanted to turn counterclockwise, and the two kind of canceled out each other. And I ended up seeing this really inconsistent subpar performance in my devices. I was, for a moment, still kind of stuck in my inertia and trying to think, well, how do I kill that effect? How do I get rid of this counter effect and just make my device work in the way I want it? But then one night it occurred to me, well, if that effect is so strong that 8 out of 10 times it dominates over the effect I want, maybe I should go for that. And I looked into the literature a little bit. I figured out what was the physical origin of that effect that made the loop go, counterclockwise. And within a month, I had a working device. that formed the basis of my PhD thesis. So I think the thing I learned there is All Out and Vero had talked about, you got to think out of the box, and you cannot let go of an observation just because it's not what you expected or not in the norm of what you designed or set out to find. It's really, you know, the serendipitous things that sometimes gives you the main finding, or, you know, the satisfaction, the success in your research. Yeah, that's my story.
Okay, so now it's my turn to share my horror story with everyone. So this was actually when I was already starting a postdoc, and out of my thesis, you know, usually you have 1 or 2 or 3 papers coming out of your thesis. So this was, so the first one was published, and once I got my thesis, and I was working while being a postdoc on my second one. And about 2 or 3 weeks before I published my work, I realized that somebody else published it in a by far more generality, and it was a by far better result than I was supposed to do. This was a team of mathematicians at York University in England. And this was pretty nice. I mean, this was pretty devastating, because this is the time you're looking for a job. And I said, okay, so my CV is now going to be pretty miserable. I have 1 paper published and 1 paper which was basically totally overshadowed by another paper. But there is a silver lining. So I said, okay, so instead of getting, obviously, nothing I could do. I mean, this was by far better result, and it was, the methods by far superior to mine. So there was nothing, I mean, I could say I could solve it differently, yeah, but I could solve it differently in a much more primitive way. So the silver lining is, I said, I got in touch with those researchers, the other researchers, which I knew of but never met. And the nice thing about our field, I'm guessing the same for most of the other fields, I mean, people are nice. And so I said, hey, listen, you stole my result and now you're leaving me like this. And so they invited me over. I stayed there for more than 3 weeks in York, and ever since then we've been collaborating. So, and again, this comes to what everybody else has said. I mean, again, of course you can find some oddballs and some nasty people in every field. I mean, in every company, in every, I mean, but most of the people doing research, and I mean, they're nice because they're coming from the same motivations. I mean, it's not for the glory, it's not for the money, it's not for the, it's for the love. And so, no, I'm kind of underplaying it. It was pretty devastating, to be honest. But at the end of the day, years later, it turns out to be a good experience. I mean, it turned out that I met those amazing people, and we, ever since then, been doing a lot of research together. And so this also should be a lesson from this. So I don't know. So the lesson is, it happens. Most of the times you can make the mess. I mean, just get in touch with whoever's doing it, and you know, something good will come out of it. And if not, then just, you know, you're too young, I can't say. Just, you know, keep on going, and everything will be okay. That's it.
All right, thank you, Dr. Fishman. So that brings us to the end of our prepared questions, and it looks like we have some audience questions. So for these audience questions, you guys are free to either all answer them or you individually answer them. So I guess the first question, I think Dr. Schemmer indicated that you want to answer this one live. Is it possible to work in fundamental physics without programming heavily with computers?
Oh boy, yeah. So I answered a few of the questions, but I really feel that for all the questions, they deserve live answers, because you know, they're way too long than just typing 1 or 2 lines. But I'll just say this, and I hope Oliviera will agree with me. Physics today, and astronomy included, of course, can't really live without computers. Computers are really fundamental to all that we do. Not necessarily the word programming or programming heavily. Yes, we do. I mean, Oliviera probably programs a lot more than I do as a physicist, but I would say scripting maybe, but you got to love your computer, because this is really your instrument. You know, again, as an astronomer or a physicist in the past, if your instrument was the spectrograph or the telescope, you don't get to meet those devices and instruments too much anymore. For example, if you're a high energy physicist, speaking about fundamental physics, then you know, your main instrument lies under the city of Geneva in Switzerland, where thousands or actually 10,000 scientists work around the clock. Not everyone will get to go there. You don't always get to feel the data or feel the instruments. So you really have to do things remotely. You really have to get a bunch of data, analyze it quickly, and produce some results. So you gotta love your computers, you gotta love your scripting, you gotta love your programming. And if I may add another aspect here about the interaction with students, my second question to students, obviously after are you enthusiastic, are you obsessed with this, and so on. My second question is, what is your experience with computers? And the usual answer I get, again, not offending anyone here, but from everyone, graduate students and undergrads alike, is, well, I can run a few programs through Windows, I can write a Word document, and I can create a spreadsheet in Excel. And that is pretty much it. And then we chuckle and we say, okay, fine, let's get you started with some scripting and getting to know some software and getting to know Unix and the Mac and, you know, other operating systems. So the short answer is, as we progress and as we evolve, STEM in general, but physics and astronomy in particular, are moving heavily towards what we call the big data era, where a lot of programming, a lot of computing is needed. This may also tie into another question I saw on the screen about theoretical physics. What should I do, theoretical physics or experimental physics? I would say in both fields or in both directions, computing will be needed. But more so if you want to be a theoretical physicist.
Yeah, if I can add on that, so true, you can still do experiments or pen and paper theory. I mean, that's still an option in many fields, but computers are really the third leg of scientific research, and they're going to be there for a long time. Especially because toward the main scientific advances in recent years, I mean, will be even more relevant when you guys will be doing research. So we have machine learning that it's true, is a trendy word, but is really changing some of the ways we are doing things, especially since the amount of data that we have is becoming so huge that we are really trying to find, I mean, there are already ways to make sense out of this massive data. And then the second thing is quantum computing, which is nowadays a reality and is going to be changed again. And we do a lot of things in the near future. So computers are going to be really relevant. So, I mean, even if you want just to do theory, pen and paper, then you probably need someone to run simulations to prove that what you've done is relevant. Or in chemistry, there is this software that is called Gaussian that allows you to simulate the properties of molecules, and is very user-friendly. And I mean, since probably 20 years, any scientific paper in chemistry needs to have some Gaussian calculation to support, even if it's an experimental result. The calculations are always there to support the experimental results somehow. And so it's going to get even more relevant in the future. And
yeah, if I may chime in here, I totally agree with Oliviero. As a chemist, you got to know some computational tools these days. Almost all of it, well, I wouldn't say all of it, 80 to 90% of the papers that I see in recent publications involve some aspect of simulation and computation. Also, I would add that not only are we using computers to simulate a chemical system, we're actually adopting the how do I say, the thinking of coding and programming in creating new molecules. There are in fact a stream of papers coming out in the past 2 years talking about looking at synthesis and designing of molecules as a algorithm or as a programming problem. There's actually one paper that goes that far as to design a programming language entirely based on molecules. They put them together, they write, say, a forks, 4 loops, and they end up building a complicated molecule in an automated way that you would never imagine would be possible with a conventional synthetic method. So it never hurts to know coding.
And to support what Oad said, there is no need to be super proficient in programming languages. I mean, scripting a user-friendly language like Python, that would be enough to get most of the things done, and maybe knowledge of a Unix-based operating system. By the way, so the physics department introduced an undergrad intro-level course on programming for science that I'm currently teaching. I don't want to advertise it too much, but this year there are very few students, but I think it's a good way to start learning some of these things.
Thank you all for your responses. Our next Q&A question is, for someone trying to decide between pursuing theoretical and experimental physics, what advice do you have?
Maybe Oliviero?
Which Q&A question is that? Because I'm not sure I saw it.
I think it's in the answer.
Yeah, it appeared, I wanted to answer it online, but then I think it went over to the answered ones for some reason. I kind of hinted about it earlier from my perspective, again, as an observer, not an experimentalist. So you may hear a little bit of background noise in my house. There's someone working drilling, and you can imagine that if he's drilling downstairs, it means that I didn't want to do it. I probably can do it, but I don't want to do these things. I also didn't want to be a physician. I can't see blood, you know, and other things. So there are things that I know I can do and like to do, and there are things that I know that I don't want to do, even though I can probably do them, like work in a lab, work as a chemist, and mix solutions and all that, but I wouldn't like to do it. I chose to do something that is cleaner, that you don't get your hands dirty, that you do a lot of simulations, computations, data analysis. Everything is nice and clean. You work with clean instruments. You don't even have to travel anymore to the mountaintop in the middle of the night with 20-degree temperatures on the mountaintop. So if you feel more comfortable sitting wherever and whenever and analyzing data on your laptop, then probably theoretical physics is for you. And again, it allows you this flexibility, especially during the pandemic, where you'd say, I don't really care what's going on in the world right now, because as long as I have a good and reliable Wi-Fi connection, I can analyze data, I can download data, I can work on my papers, I can do my research without any disruption whatsoever. Whereas if you're an experimentalist, and you need to go to your lab, if your lab is, say, flooded, like one of our labs just flooded again in physics a few weeks ago, then you're stuck. You're encountering obstacles and problems. So it's really, I think, a matter of personality. In both cases, you'll reach the same conclusions, same results. It depends on what kind of person you are.
Yeah, so for me, it's a question of maybe the state of mind. I like to be able to control every aspect of what I do, and I already feel uncomfortable with running simulations on real systems. I prefer to develop methods because I know what the final result should look like. I know better how to control every aspect of it. It's a bit more of a obsessive compulsive kind of behavior where I want to have everything really under control on what I do. I feel with experiments, there are so many variables that enter the picture that it's less so, but again, it's a question of your personal attitude, I guess.
I think this question was also answered, but if anyone wants to chime in, how does your research specifically apply to other industries such as the medical and pharmaceutical? And there was also a similar question that asked how your research applies to the real world and impacts society.
I think I answered both. I mean, I can elaborate if that's okay, if you want. So I think the question that the first one about pharmaceuticals was, how do you apply a set of skills, or if you, let's say if you worked in one area and now work in a completely different area, and again, someone can correct me if I'm wrong, if I misinterpreted the question. But what I always tell my students when they start working with me, you know, they're usually and rightfully concerned about what the future holds, because they're coming in to work on black hole research, right? Perform observations or analyze observations that measure certain properties around black holes. And they know almost for a fact that when they graduate and move on and maybe go work for corporate America, they will not be researching black holes anymore. They will likely be working on silicon chips or maybe in an insurance sector. So they, what I tell them is, don't worry, relax. Have you read material and planned to learn about the subject matter that you're working on right now? And if the answer is yes, then well, that's good. You did that about black holes as well. Did you analyze data? Did you reduce data? Are you going to reduce data? Yes. Sure. Are you going to summarize your data in a paper or a report? Yes. Are you going to present your results in front of an audience, like a board meeting? The answer is yes. If you answered yes to all these questions, then it doesn't really matter if you worked on quasars, the kind of objects that I work on, or you worked on silicon chips, or you worked in the pharmaceutical industry. Once you acquire a set of skills in one area, you can easily and in a straightforward manner apply them somewhere else. The main important thing to keep in mind is that when you're in college, you learn how to learn. You don't necessarily learn a set of skills that would take you to do something else later on. That's probably a trade school. But when you're in college, you learn how to get data, how to get your resources, how to find the literature, how to do the analysis, who to ask, where to ask, and so on and so forth. These are the important skills that you need while you're a student.
Okay. If no one else wants to chime in on that question, I think it's around 5:30. So now we'll transition to the networking part of the panel. And I know there's still many questions, or I think there's a few questions that have not been answered. So students, feel free to take those questions with you to the networking rooms. And I will be sending the links to the networking Zoom links in the chat. And professors, just feel free to paste that link or click it directly, and it should take you to your own room that one of the RO execs will host. And students, feel free to hop around from rooms, speak to the professors, and ask any questions you may have.
I'm having some difficulties accessing that room. It tells me I can't. Oh, do I need a password for that?
Is it asking for a password, or is it saying?
Or maybe I have to leave the meeting first. Let me see. I think it asked for a password. Yeah, it's asking me for a password. Trying again.
Oh my God. I need this. What is I doing?
I'm gonna leave and start the room for Andresi.